Greetings, my name is Veysel Yusuf Yılmaz. Today I'm going to present to you two applications created for the Introduction to Algorithm course. In these applications, we mainly focus on sorter algorithms, so we try to visualize these algorithms and give some intuition about them with some animations. So here, the first application is an Android application written in Kotlin language. We have two screens here. The first screen is the home screen and the second screen is the sorter screen. The home screen is just a screen that gives some information about the application, the course name, the application, and the algorithm names. So of course this page is just solely created for the presentation purposes. Of course, if you want to publish our application in the market, we can delete the screen. The main screen here is the sorter screen. We have here some sorter algorithms: bubble sort, insertion sort, heap sort, counting sort, radix sort with bucket sort, merge sort, and quick sort. Numbers presented as bars. The height of the numbers present the magnitude of these numbers. We can add numbers. We can generate numbers here, random numbers, Fibonacci sequence, prime numbers, some special number sequences here. Of course, we can add more here. Of course, also we can add numbers manually here. For example, here we can add 75. We can delete numbers with our fingers swiping up here. If we click on any bar, we highlight the bar, so number is presented as text here. This feature is especially useful when the sequence size is big and we can't fit this number information here. For example, let's add 25 random numbers. Minimum and maximum values are default for example 1 and 1000. We can change this. Minimum value can be 50, for example. Maximum value can be 2002, for example. As we can see here, we can't fit the information here as text, so when we unclick it, we can see this number is 1025. So let's see how the animation works. If we start with the bubble sort, let's sort. Here, as we can see, all iterations of the sorting mechanism is shown with animations. We can change the speed of the animations. We can slow down here if you want to see better. We can speed up here. We can stop the animation, and also we can rewind the animation. Also we can stop and turn to the beginning. So let's see the insertion sort. Here we can see actually how the animation works. Clearly we can see the intuition. We can have intuition about the insertion sort. We bring the smallest number we encountered to the beginning and we iterate this process. Let's speed up. Here we have nice animations, as you can see. We can clearly see how insertion sort works. Let's create prime number sequences between 20. Show me the prime numbers between 20 and 122, for example. Of course, this list is shuffled, so we can sort this list. Let's use the heap sort here. Let's slow down to see better. So we first try to obtain the heap schema here, right? When we obtain the heap schema, the biggest numbers appears at the front, so we can swap it to the last end of the list and we have a sorted list. So we swap, we bring the biggest numbers to front and we swap to the last. So let's speed up. And we have here a sorted list. So let's see the counting sort on the same number array. You know, counting sort works differently from the algorithms we have seen so far. So it is represented freely, of course. This is the only way that we can represent. Let's start from beginning. As we can see, we counting the numbers actually. This is how the algorithm works. We can see here. So let's create Fibonacci sequence here. Of course, Fibonacci sequence grows very fast, so we can't have a very big, sequence here. Let's add 12. As we can see here, this of course shuffled list. Let's try the radix sorted box sort, how it works. Here, each iteration we sort our list with using box sort. Each iteration we getting closer to the sorted list. And here, the last iteration we have the sorted list. Let's create a list here and use the merge sort. If we remember the merge sort, we divide the list into the smallest part, and we sort this smallest part and we merge this up and we obtain a sorted list here. This is the original merge sort. This is not some other you see on the internet. In place merge sort they call it, but this is the original merge sort. As we can see here, we can see each iteration of the merge sort. Let's speed up. Here, let's use the quick sort here. Quick sort is really fast. We can try the big number sequences here. Let's add 60 numbers and use quick sort. It works like a magic. So this is how the Android application works, and let's look at the Python application here. Let's close this, and we have here our Python application. Let's start it. Here we have Python application. As we can see here, actually the working mechanism of this application is very similar to the Android application. The code logic here is very similar to the Android application, but there is little differences. We can create arrays here. Let's add arrays like this, and we can sort. We can change the. We can choose the animation here. Let's choose the heap sort. We can of course change the speed here. Let's speed up. We can pause. We can go back, like Android application. Of course, animation in the Android is better than this. Also, we have here an additional feature here, compare feature. This feature compares all the algorithms we have here. Let's use it. As we can see here, the slowest is the bubble sort, this one. Then insertion sort. These two algorithms grows exponentially when the size of the array grows, but the other ones, almost linearly, logarithmic scale. As we can see here, the fastest are counting and quick sorts. So this Python code is actually public, available in GitHub. So I will put this link on the video. Thank you for watching, and see you soon.